Okay, so I want to look at a few more examples in the homework. And like I know that I think I titled this video Arithmetic Sequences, but I know some of them are going to also talk about recursion or things that are defined recursively, like number 7. And recursive just means you have to rewrite them each and every time. And just as a side, one of the more famous recursive sequences is the Fibonacci sequence, and you probably have come across this at some point in your in your math study, or even like maybe pop culture if you ever watched like the Da Vinci Code or things like that. But the Fibonacci sequence starts with 1 1, and then you just add the two previous numbers. So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8. And in other words, like it's defined as the first term is 1, the second term is 1, but then any nth term is equal to the sum of the two previous terms. That's an n minus 2. So if you wanted, let's say, like the third term, you'd say, oh, that's the second term plus the first term. Now, if you wanted the 50th term, you'd say that's the 49th term plus the 48th term. But the problem is, unless you know what the 49th and 48th term is, you can't get the 50th term. So that makes recursive sequences, although maybe easy to describe locally, right? Like, oh, within this area, I know how to get that next term. But if you want to extrapolate to figure out what's that 100th term, it makes it a little bit more challenging. So just to know that is a little bit different in terms of of a recursive sequence. Now, this is a recursive sequence that tells me in example 7, the first term is 2. And then it says to get to the next term, you do -1 divide by that term. I realize I just said it's really hard to go out to like the 50th or 100th term without knowing the previous terms. And now all of a sudden, not only do you have to get to the 100th term, but then add them all up. So let's take a look at what this recursive sequence really is, because perhaps there's a little bit of a pattern to it. And that's sort of my suggestion for a lot of these problems in this unit. When you're a little bit stuck, maybe start drawing out a pattern and drawing out what those numbers look like. So first term is 2. And then to get to the next term, we're going to do -1 divide by that term we just did. So -1 over 2. And then to get to the next one, we'll do -1 divide by that. So -1 divided by -1/2. Well, -1 divided by -1/2, that's really just 2. So then get the next term, -1 divided by that. Oh, so -1/2. And then -1 divided by that. Oh, we're back to 2, right? We just did it. So it looks like this sequence, 2 and then -1/2, and then 2 and then -1/2, and then 2 and then -1/2. So even though it was originally defined as a recursive sequence, I definitely see a pattern. It's also an alternating sequence, right? So if it says find the sum of the first 100 terms, well, if it just alternates 2 and then -1/2 and then 2 and then -1/2, of those 100 terms, 50 of them will be 2, the value of a 2. 50 of them would be a value of a -1/2. So looking at what this sequence actually is gives us some insight that there are 50 of the terms that are 2s, and there are 50 of the terms that are -1/2. So 50 times 2 is 100. 50 times -1/2 is -25. So then we know that the total sum would be 75. Okay. Now the next example, just to kind of go about the little bit of vocabulary, inclusive versus exclusive. So it says find the sum of all integers between 325 and 550, inclusive and then exclusive. So if it's going to be inclusive, you're going to include the endpoints. So you're going to start with 325, and then 326, all the way up to 550. So you're going to include those. So I can look and say, okay, well, between 325 and 550, that's 175 numbers. But then I'm going to add one more. So it's 175 is our span, or is our distance, and we add one more to find how many numbers there are. So it's 176. So I'm counting 176 numbers. And so then I could say, well, then that's equal to the first term, which is 325. Who's that guy? So first term plus the last term, which is 550, divided by the number of numbers, 176 over 2. Right, so then you could type that in. 325 plus 550 is 875 times 176 divided by 2. So 7,700. Sorry, 77,000. Now, if you're doing this exclusively, that means you're not going to include 325. The first one you would include would be 326. That's the next number. And then you'd go all the way up to 549. That would exclude your endpoints. Now, you could do this the same way. Like we had 176 numbers. You take 2 out, so now you have 174. And you could say, well, my first number is 326, and my last number is 549, and I know I have 174 numbers now, divide by 2, to get my result. Or you could realize that, well, this is the sum of everything, including the endpoints. So if you just take that sum of 77,000 and take away 325 and 550, you could get that sum as well. So minus 325 minus 550, which is equal to 76,125. So either way, you'll get to that same answer. Okay, and then I wanted to do another recursive problem here, number 15, just to kind of look at this. Okay, so it's the sum of the first 5. Here it tells us what the first number is and the second number is, and it says to get to the next term, the nth term, we're going to square the most immediate term that came before it, and then add it to the second term that came before it. So to find a sub 3, I would square a sub 2, which is 2, so 2 squared, and then I would add it to the first term, which is 1. So 2 squared is 4 plus 1 is 5. So I know the third term is 5. Now to get to the fourth term, I would square the most immediate term, so it's the third term, which is 5, so 5 squared, and I'd add it to the second term that would have come in the sequence right before it, which would have been 2. So then 5 squared is 25, plus 2 is 27. And then to get to the fifth term, I would square the term that came right before it, so 27 squared, and then I'd add the term that came 2 before it, which is 5. Okay, so then 27 squared is 729, add 5 is equal to 734. Now, that's it. It just wants the first 5 terms. But the thing is, even though this is sigma notation, right, that's just an abbreviation for these first 5 terms, I have to add 1 plus 2 plus 5 plus 27 plus 734. There's no it's not arithmetic. There's no pattern in the recursion. I simply have to add 1 plus 2 plus 5 plus 27 plus 734. So I get 769. So again, just another example of using that recursive definition to help solve for that problem. Okay, and I think there might be one more. Oh yeah, one more recursive problem. So then again, finding the sum of the first 60 terms, perhaps there's a pattern. So let's look. So the first term is 1. The second term is 3, and to get the next term, you find basically the quotient of the previous 2. So not the sum, like a Fibonacci. So we have 1, then we have 3, and then notice the order. It's the most immediate divided by the second most immediate, right? So 3 divided by 1 would be 3, and then I do 3 divided by 3, which is 1. And I was like, oh, nice pattern here. 1 divided by 3, 1/3. 1/3 divided by 1, 1/3. 1/3 divided by 1/3, 1. 1 divided by 1/3, 3. Right? Because think about 1 divided by 1/3, you multiply by the reciprocal, 3. 3 divided by 1, 3. 3 divided by 3, 1. Okay, so now I start seeing a pattern, right? 1, 3, 3, 1, 1/3, 1/3. 1, 3, 3, 1. You're going to get 1/3, 1/3. So, right, 1/3, because 1 divided by 3 is 1/3. 1/3 divided by 1 is 1/3, and then we'd repeat. So it looks like every 6 terms repeats. So it's a little bit more than the other recursive one, but there's still some repetition every 6. So if I'm looking for the sum of the first 60 terms, that's 10 groups of 6. So if I could figure out what the sum of 6, like the first 6 are, I would just multiply that by 10 because it's going to repeat itself. So if I add 1 plus 3 plus 3 plus 1 plus 1/3 plus 1/3. So 1 plus 3 is 4 plus, right, another 4 is 8. So it's 8 2/3. So it's almost 9, right? So 8 2/3 or 24 by 26 thirds. Okay, so the sum of the first 6 terms is 26 thirds, and I've got 10 of those groups, so just multiply by 10. So that I could write that sum as 260 out of 3. Okay, so again, when you see a recursive sequence in this particular section, look for that pattern by simply listing out the first several numbers. And in one of the examples, we only had to list 2. In this particular example, we had to list out 6.